All right, so last video dealing with rank. Let me go ahead and I'm fairly positive this is what I said at the tail end of that last video. But sometimes if I hear background noises, my ADD, I get distracted, and I can't remember what I said just a second ago. So let me just make sure, just in case, I want to respond to the example 2, and notice that I've written out the basis for the row space and the basis for the column space. And let's count how many vectors are in each. There's 1, 2, 3 vectors in the row space, 1, 2, 3 vectors in the column space. So therefore, what? So therefore the dimension, start with the row space. The dimension of the row space is 3 vectors. And the dimension of the column space is also 3. Now, that's not a peculiar part of example 2. In fact, let me go back to where we left off. In fact, the dimension of the column space and the row space of some m by n matrix are equal. Now, this common dimension, all right, which is the rank of A, also equals the number of pivot positions in A. If you go back and look at example 2, there was exactly 3 pivots. Okay, dimension of column space was 3, dimension of null space row space was 3, and there were 3 pivots. So that's actually very helpful because, and it's going to be helpful coming up in this next example. So the equation that we can build from that is as follows. So the rank of A plus the dimension of the null space of A is equal to n. Now, remember, if it's an m by n matrix, so n. So the rank of A plus the dimension of the null space is equal to n, right? Because, so very helpful, a very helpful equation. So let me show you how we can think about this when I don't give you a matrix, right? So notice this type of question, it's for some arbitrary matrix A. And what we're saying is A is a 7 by 9 matrix. Now they give us a little bit more information. They say if A is a 7 by 9 matrix with a 2-dimensional null space, okay. Now that would mean 2-dimensional null space. That would mean there are 2 vectors in the basis of the null space. But they ask, what is the rank of A? Okay, so let's see if we can use that. I'm going to go ahead and grab that theorem from the previous page, and let's see if we can use that to our advantage. So remember that it said the rank of A plus the dimension of the null space of A equals n. Now let's think about what we have in this problem. Well, the fact that it says a 2-dimensional null space, that means the dimension of the null space is 2. So I know I can place 2 here. Now I don't know what the rank of matrix A is because I don't even have a matrix yet, right? So in other words, if you're thinking, how do I do this if I don't have a matrix to go through and row reduce? But I do know that it's a 7 by 9 matrix, so I know n. So you imagine taking 9 and dropping it in for n. And that's exactly what I'm going to do right now. So the rank of matrix A plus the dimension of the null space, which we saw as 2, must equal 9. Therefore, subtract 2 from both sides, the rank of A is equal to 7. All right. Now, let's take a look at part B. So this question reads, could a 6 by 9 matrix actually have a two-dimensional null space? Could a 6 by 9 matrix actually have a two-dimensional null space? Well, let's go ahead and write that out, right? So let's just like we did in the previous problem. So rank of A plus the dimension of the null space of A is equal to n. And let's go ahead and plug in the information that we have available to us. So again, we're plugging in 2 here. We're plugging in 9 here, just like prior. So we ended up with a rank of A was equal to 7. But now let's answer the question. Could a 6 by 9 matrix have a two-dimensional null space? Well, the answer is no. Right? And you could look back to our section in 4.5, but the idea is the dimension of the column space can't exceed the number of pivot positions. So let me ask you this. So this is 6 rows by 9 columns. If you have 6 rows, what is the max number of pivot positions that you could have in 6 rows? Well, the maximum is 6. You could have a pivot in every row. So there's no way that this makes sense if we have 7, right? Because you have the maximum number of pivot positions you could have is 6. All right. So I think we've pretty much got under control this, or at least I hope we have some of this vocabulary and some of these ideas under control. I'm going to do one more for you, and then the homework will hopefully start to solidify these ideas. Now, it's only later in chapter 6 where we actually start to study the geometry of the row space and the geometry of the null space. And I'll just tell you just right now, we're not in that chapter, but they only have the 0 vector in common, and they're actually this the spaces, they're actually perpendicular to each other. But for our purposes, the last piece that we want to be able to do is we are given a matrix A, and what I'm going to do is I'm going to go ahead and RREF matrix A, because I know that where this question is going, I'm going to need to do it anyway. So that's 1 0 0 0 0 0 0 1 0. Okay. Now let's go ahead and answer. I can read the question to you, but here's the information that I want to be able to answer. Let's start with the rank. Okay, so let's look at the row reduced form of matrix A. Let's find our pivots. How many pivots do we have? Well, we have a pivot here. We have a pivot here. So there's 2 pivots. That means the rank is 2. Okay, let's go ahead and find the basis. find the basis for, well, let's go ahead and do the column space. All right. Well, if there's two pivots, so column 1 is the pivot column, column 3 is the pivot column. So that means that we want to go back to the original matrix and grab column 1 and column 3. So let me write that. So that's 3, 3, 4. And what is that? -1, -1, +5. So that is our basis for our column space. Now let's look at we'll do the basis. Actually, we'll do the basis for the null space right now. All right, well, if when you're forming the basis for the null space, you could now well, I don't want to. I tell you what. Why don't you should try this to see if you can do it, because I shouldn't be just leading you this far. But if you think about what is the free variable here, right? So in this case, what you have is you have x sub 2 is the free variable. So when you think about it, when you write that as x sub 2 multiplied by some vector, now we'll figure out what vector that is, but think about it as if there's only one free variable, then there's only going to be one vector in the basis for my null space. Now, what is that vector? Well, let's think about it. I mean, think about it as if you are, you can think of it as you're factoring out you can think of it as you're factoring out a free variable, if you would like to think of it that way. I'm going to go ahead and answer this for you. I think you should be able to get to this from where I'm at. And that would just be 0, 1, 0. All right. So this is the null space, a basis for the null space. And the last one that we got to be able to tackle is the basis for the row space. All right. Well, how many vectors do you think should be in the basis for the row space? Well, we've already talked about that it should match the basis for the column space, right? So there's 2 vectors in the basis for the column space, so we definitely should have 2 vectors in the basis for the null space. And what we're going to do is we're just going to grab the first 2 rows. Okay, so that's gonna look like this. Apologies, let me use my braces here. So let's do 1, 0, 0, and 0, 0, 1. There you go. And that will conclude Chapter 4. I'll see you again for Chapter 5.